You spin a coil and you get electricity out. But why does the current sometimes fight back, which slows our coil down? This is physics related to generators, counter torque, and eddy currents. So first, this is how a generator converts mechanical energy into electrical energy using electromagnetic induction. When you rotate a coil inside of a magnetic field, the flux through the loop changes, and this induces an EMF. That's Faraday's law, right? And this EMF from our spinning coil, we have a formula for it, which I'll put on the free cheat sheet in the description, but what it is EMF equals NBA, this symbol, sine this. And let me break it down. N is the number of loops inside of your coil. B is the magnetic field. A is the area of your loop. And this symbol, which is mini case omega, I'm just going to call it W. It's angular velocity. And sine is a sine function, which means that voltage goes up and down, right? Sine waves. And what this means is that it's an alternating current, AC. This is, again, angular velocity, and this is time. This and every other formula we'll look at today is on the feature sheet in the description, and we're going to use it to solve problems later on. When you have some kind of coil and there's a field caused by some magnets, and it's rotating like this, the motion is perpendicular to the magnetic field. So the only velocity component that matters is the perpendicular velocity component, which is sine. And we get this formula. EMF equals 2NP VL sine. What is this? What I've done here is derived EMF from coil motion. And if your coil is rotating with an angular velocity of W, then the angle is equal to WT, which is like that. And then EMF becomes equal to NBA's angular velocity sine the angle. And these two formulas confirm what we observe, which is a voltage that follows sine. This is on the free cheat sheet as well. And let's go through an example problem with the formulas that we've been talking about. Say you have a 50 Hertz generator with a coil area of 0.025 meters squared. So that's this area. It's rotating inside of field with a strength of 0.18 Tesla. What is the required number of loops to generate a peak EMF of 200 voltage? Let's link up what we know and what we're looking for. What we're looking for is N, because that's the number of loops. And take our EMF formula, which is NBA, angular velocity, and we can rearrange for N, giving us N equals EMF over BAW. And EMF has a little zero because that means maximum EMF. So here's our formula, and what do we know? We know the magnetic field. We know the area. We know the EMF we're looking for. We just need angular velocity. Angular velocity, if you think back to circular motion, it's given with 2 pi f, with f being frequency. And our frequency is 50 Hertz. So this gives us an angular velocity of 314 radians per second. Now, if you plug everything into our formula down here, because we know everything, then our answer is this. So 200 for EMF, field is 0.18, area is 0.025, and angular velocity is 314. Then we get roughly 142 loops. So what we've done is to find this EMF voltage, we now know the amount of loops in our coil. Now moving on to the next concept, which is back EMF in motors. Motors work in reverse. So instead of a spinning coil that creates electricity, you apply voltage to make your coil spin. But as it spins, the flux going through the coil will change because Faraday's law, when you rotate it, it affects the flux. This will induce EMF that opposes your input. What this EMF is called is back EMF, and it's Lenz's law again. The faster your motor spins, the more it's going to resist its own input. The back EMF is proportional to the angular velocity, which is how fast it spins. Let's go through an example. Here I've drawn a little circuit, and what it represents is a motor. The motor has a resistance of 4 ohms. It's connected to a battery, the 120 volts, and at full speed, the back EMF that's induced is 102 volts. Let's solve for two things. First, what is the startup current? And two, what is the current at full speed? The startup current means there's no back EMF yet, so we can simply use Ohm's law, which is voltage over resistance. The voltage is coming in as 120. and the resistance is 4, giving us 30 amps as the startup current. How about when it's moving at full speed? When it's moving at full speed, we have to include the back EMF that occurs. So the current becomes voltage minus your back EMF divided by resistance. Ohm's law, but voltage is going to be different because we're spinning harder. This is 120 minus our back EMF of 102 divided by our resistance, giving us 4.5 amps. So the takeaway here is that the current drops drastically once the motor reaches full speed, and this protects circuits. The next concept I'll teach you is counter torque. So counter torque in generators, what it is, say our generator powers the load and current is flowing through a coil. The current in the magnetic field produces a force opposing the motion. Let me draw this for you. So if a generator is powering a load and a current is flowing through a coil, the current in the magnetic field will produce a force that opposes the motion. This is called counter torque. You need to apply real mechanical effort to keep a generator spinning. The more current that gets drawn, the more torque that's required to overcome the resistance. So next, I'll teach you about eddy currents. If you study fluids, you remember that eddy currents come from turbulence. But in this context, say a metal is moving through a magnetic field. It can induce currents inside the metal itself, even without wires. And these eddy currents create their own magnetic field that are opposing. Remember Lenz's law. This creates drag and it resists motion, which means some mechanical energy is turned into heat. This is used intentionally in things like braking or damping systems or induction cooktops. But if you don't suppress them, sometimes they can waste energy. So to wrap it up, this whole system is all tied together by 4 things. One is Faraday's law, which is motion to EMF. Second is Lenz's law, and Lenz's law says that EMF opposes the change. Back EMF, which says that the generated current pushes back. And last, eddy currents. Eddy currents resist motion even inside of solid metal. So the deeper you go, the more nature is going to try and conserve and push back.